So today we're going to be looking at performing conversions within the metric system. Okay, so I'm going to give you a bunch of different prefixes that we use. So I'm going to start off in the middle here. So right in the middle, that's where we have our base measurement. So this might be something like meters, or it could be it could be liters, or the one that we actually use quite often and you don't really think about it might be bytes. If we talk about computer information, a standard size is the byte. Okay, so that's kind of where we are in the middle. So we've got things that are bigger than meters or liters, and we've got things that are smaller. Okay, and so we have these different prefixes. So this is kind of our middle ground. So the different prefixes that we have, and I'll kind of use this number line or a line to show you, and you'll see why in a second. So if I get a little bit bigger than a meter, I would get to decameters, okay? And then the next one would be hectometers, and then K is the prefix for kilo, so kilometers, right? K-I-L-O. And then after that, there's a little bit of a break, and we get to our next one, which is M, so that's mega. And then as we move over again, we get a capital G for giga, okay? And each line that I move over represents a factor of 10, okay? So every time I move one line over, I increase by another factor of 10. So now that's 10 squared, and then kilometers is 10 cubed. And so if we think about kilometers to meters, kilometers, there's 1,000 meters in every kilometer, and that's because it's 3 of these lines away. Okay, so mega is 10 exponent 6, giga is 10 exponent 9. Okay. Now, we don't just have things that are bigger than meters or liters or bytes, okay, but we also go backwards the other way, okay? So if I move one to the right, then this is a deci is the prefix, okay? And then C is centa, so like centimeters, right? And then we get M for milli, so we've got millimeters or milliliters, which is what you'll commonly see on lots of cans of pop and things like that. And then as we go from there, the next one that we have is, this is micro. Okay, so we've got micrometers or microliters. And then we have N for nanometers. Now this one, I always forget the name. I think it's a mu. It's a Greek symbol that we use for that one for micrometers. Okay, and so as we move to the right, instead of it increasing by a factor of 10, now it's decreasing by a factor of 10. So that would be 10 with an exponent negative 1, and 10 with an exponent negative 2, and negative 3, and then we get to micrometers, and it's negative 6, and nanometers is 10 with an exponent of negative 9. Okay, so the prefixes tell us how far away from that central measurement we are. Okay, so there's a few different ways to do conversions. I got 3 different methods. The first method is to simply use this same number line or this metric number line, okay, where I've got my base measurement in the middle. Okay, so I'm thinking of my base measurement. In this case, I'm going to be working with meters. Okay, so if I wanted to change 4 kilometers into millimeters, I look at my prefix K, kilo. So here I am here at that K. Now this is a bigger measurement than the M for millimeters, right? I got to move all the way over to here on my number line. So I got to go from K to M. And since I'm moving to the right, I'm changing my big measurement into something that is smaller. So there's going to be lots of small stuff inside that big measurement. So I'm going to count how far I move. I move 1, 2, 3, 4, 5, 6 lines on this metric number line. And since I've moved 6 spaces, that represents a change of 10 to the exponent of 6. So I'm going to take my 4 kilometers, multiply it by 10 to an exponent of 6, and that gives me 4 million millimeters. Okay? Let's look at the next one. I've got 6 micrometers, and I'm going to change them into megameters. Okay, so now I'm starting with a small measurement and changing it into a big one. Now when I start with the smaller measurement, that means it's going to represent a very, 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 very small portion of the bigger measurement. So this time I'm moving to the left on my number line. I'm moving 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines. And since I've moved now to the left, I'm going to say that the conversion is 10 with an exponent of negative 12. So I'm going to take my 6 times by 10 with an exponent of negative 12, and that would actually be a fine way to leave it, because in scientific notation, that's much simpler than looking at our 12 zeros. What am I at there? I think I'm at 11, and then the 6, and then the megameters. Okay, so this one is a little bit easier to look at in scientific notation. Okay, so that's one way of converting, is using the metric number line, but that requires you to have the number line, or at least have it memorized. Most of you are probably pretty familiar with using proportions, and this is probably how most of you would go about doing it. If I want to change 350 centimeters into meters, I would start off by saying, well, I know in every 1 meter I have 100 centimeters. So how many meters do I have in 350 centimeters? Okay, and this one I would simply say, well, to go from 100 to 350, I times by 3.5. So I'm going to do the same thing to keep it proportional, and I would get 3.5 meters. Okay, you can also use that dreaded form of something that we said technically doesn't exist. Remember, so I could multiply these guys across from one another and divide by the one remaining, but remember that technically doesn't exist. What you're really doing is solving your equation, so make sure you would be showing your solving steps accordingly. So solving the proportion is fine, but that requires you to remember all of the different conversion factors perfectly, and I'll be honest, I forget them consistently. So I'm going to show you my favorite one, which is unit analysis. Okay, now unit analysis is great because it requires me to know just some basic conversions. I don't need to remember every single specific factor. I can do very complex things and only remember some basic ones. Okay, so I'm just going to use things where I have known conversions. So if I wanted to change 2.5 kilometers into centimeters, I don't remember that number line, and I don't really want to think about it every time. So what I'm going to do is I'm going to start with 2.5 kilometers, and I'm going to think of my kilometers almost as if it was a variable, and I want to cancel that variable. So if I want to cancel out my unit of kilometers, I'm going to have 1 kilometer in the bottom. Okay, well, what's some conversion that I know using kilometers? Well, I can always remember that 1 kilometer is 1,000 meters. And so what happens now is my kilometers are going to cancel one another, right? I got 1 up top, 1 in the bottom. If I was looking at using my exponent laws, I would be subtracting those km's, right? Km exponent 1 minus the 1 in the bottom gives me km exponent 0, which is 1. Now they're not variables, they're units, but they're canceling as if they were variables. Okay, but now I've got meters, and I don't really care about meters. I want to know centimeters. So I got to get rid of that unit of meters, and I know 1 meter is 100 centimeters. And so what this is doing is it's just allowing me to use simple known conversions to quickly change from whatever unit I have into what I'm looking for. Okay, so to get 2.5 kilometers into centimeters, I take my 2.5 and I'm going to times by 1,000 and then times by 100, and that gives me 250,000 centimeters. Okay, so I like unit analysis because I don't need to remember some of the crazy conversions. I don't need to know that there are 100,000 centimeters in a kilometer. I can very quickly get there. Okay, so I like that because it allows me to work with something like this. If I have the speed of light, which is approximately, I'm rounding, it's approximately 300 million meters per second, how fast is light moving in kilometers per hour? So I can kind of compare it to like my car, right? So if I've got 300 million meters per second, I can write it as 300 million meters per 1 second. So I put the second on the bottom. Well, I can actually use unit analysis to change all of my units in one go. So I don't want seconds, I want hours. So seconds is in the bottom. So I'm going to put seconds up top. Now I need some conversion that I know. Well, I know that there's 60 seconds in 1 minute, so I can do that. But then I don't really want minutes, so I got to put minutes up top. And, well, I know that there's 60 minutes in 1 hour. All right, so that's going to cancel out. My seconds are going to disappear. My minutes are going to disappear, and I'm going to be left with hours. So that's great. I've already changed it now, so I got meters per hour. But I also don't want meters. So I'm going to put 1,000 meters in the bottom is 1 kilometer. And I'm putting the meters in the bottom because right now meters is up top, and I have to cancel it by putting another meters in the bottom. So the only units I'm left with now, I've got kilometers and I got hours. So I'm going to get kilometers per hour. This is great. That's what I wanted. Okay. So up top, I'm going to go 300 million times 60 times 60, and then I'm going to divide that by 1,000. And when we do all of that, I need a little bit more space. We get 1,080,000,000 kilometers per hour. So that's very fast. Okay, so if I'm thinking of that in terms of my car, let's say I was going 108 kilometers an hour down Deerfoot, that means that the light is still traveling 10 million times faster than my car. I would need to travel for 10 million hours to move the same amount of kilometers as light is moving in that hour. I would need to keep driving for 10 million hours. And if I was to keep driving for 10 million hours, I don't even know if I can do that in my lifetime. 10 million hours, let's see. I've got, well, there's 24 hours in a day. Oops, 24 hours in a day. And I know that there are, we'll say 365 days in a year. Now I know we've got leap years, but I don't think that's going to make too much of a difference. So 365 days in 1 year. And when I do that, I find out that I would need to approximately be traveling in my car for 1,141.6 years. And if I do that, and I'm traveling at that constant speed of 108 kilometers an hour, that's how long it would take me to travel as far as light is moving in 1 hour. That's how many years it would take. So I'm definitely not going to live that long. Okay. So one other thing I want to show you. So how far does light travel in a year? Right? So I've got that 300 million meters per second. I'm going to change that. Now I want years as my unit, right? How far does light travel in a year? So I got to get years. So I got 60 seconds in a minute. And I've got 60 minutes in an hour. Now, if you remember that there are 3,600 seconds in an hour, you can do that direct conversion, but I don't always remember that number, so it's fine to just use the conversions that you know. There's 24 hours in a day, and then there are 365 days in a year. So I'm going to keep my meters, and then I'm going to get meters per year. Now, let's see, let's go, not meters per year, let's go kilometers per year. So I've got 1 kilometer is 1,000 meters. Okay, makes sense to talk about it in kilometers. Okay, so when you multiply everything out, that gives you 9.4608 times 10 to the exponent of 12 kilometers in 1 year. So if somebody ever talks about a light year, that's what they're referring to. They're talking about the distance that light can travel in a year. So when we say that something is a light year away, it means that it is, that would be 9,460,800,000,000 kilometers away. Okay, so when we talk about a light year, it's a distance that light can travel in a year. Okay. Anyway, I just always think that's something cool to do. Unit analysis is very powerful because I can do all sorts of conversions just using very basic conversions that I know.